Hey everybody, in this video we're going to be talking about ways that chemical reactions are represented. Now understand that chemical reactions are the things that are actually happening. Chemical equations are the ways that people represent them. We'll look at three ways: a word equation, a skeleton equation, and finally a balanced chemical equation, which gives you the most information. Now here we have an example of a chemical reaction. This is vinegar reacting with baking soda. Now, the active ingredient in vinegar, the thing that is reacting, is acetic acid. What's in baking soda, or what baking soda is sodium bicarbonate. The bubbles that are being produced are carbon dioxide. There is also water being produced, but you can't really tell since there is water present mixed with the acid. And the other thing that's being produced is sodium acetate, the chemical that's used to flavor salt and vinegar chips. The first way I'm going to describe this reaction or explain this reaction is with a word equation. A word equation tells only the reactants, the things that are reacting, and the products, the things that are produced in the reaction. It should have their phase, but sometimes does not. The word equation for this reaction would be acetic acid reacts with sodium bicarbonate to produce carbon dioxide, water, and sodium acetate. We'll look next at a skeleton equation. A skeleton equation gives the correct formulae for all of these substances involved, but not necessarily in a balanced way. It will have the phase of each substance. Remember your naming rules and your formulae rules when looking at ionic compounds and covalent compounds and acids to come up with a correct formula. To come up with the formula for acetic acid, I knew that because it had an IC ending, that the polyatomic ion it forms from would have an ATE ending. So instead of acetic acid, it comes from acetate as the polyatomic ion. And you can see that the charge on acetate is a 1- charge, and so as an acid, it would get 1 hydrogen. For the next substance, I needed another reference sheet. Because it's an ionic compound, sodium bicarbonate, it has to be balanced by charge. The sodium ion, according to the reference here, the trends for ionic charge, has a 1+ charge. And then again, on the polyatomic ion reference, bicarbonate, HCO3, has a 1- charge. And so 1 sodium with a 1+ balances 1 bicarbonate ion, HCO3. And so its formula is NaHCO3. Those are the two reactants, so next is the arrow, meaning that the products are coming up. For the first product listed, sodium acetate, recall from the reference that sodium has a 1+ charge and acetate has a 1- charge, and so its formula is NaCH3COO. There are a number of ways to write acetate, by the way. It could be C2H3O2, as long as you have the right number of atoms. Sodium does come first, however, because it is the positive ion, the cation ion, and then the negative ion comes after. Next is water. It's common knowledge that its formula is H2O. And finally, carbon dioxide. The di means that there would be 2 oxygens. And the last part in a skeleton equation is to include the phases. The phases would be either solid, liquid, gas, or AQ, which means aqueous. Acids are almost always aqueous, and so their phase is going to be aqueous. They are dissolved in water. The sodium bicarbonate you saw was a solid. If something is produced in water and it stays in water, then it is going to be dissolved in the water, and so that's why the sodium acetate has a phase of aqueous. The water, if it's produced through a reaction that heats it up and it is steam, then it is gas. Otherwise, you can see that it's cool enough to be liquid water. And finally, the bubbles that were given off were the CO2, and so it was a gas. Now this section is to use models to show what balanced means in a reaction. These are models of acetic acid and sodium bicarbonate. And what balanced means is that you could take all of the atoms from the reactants and rearrange them to make the products with no extra pieces and none needed. Now, as you could see with these models, I was able to take all of the atoms in the reactants and recreate all of the atoms in the products with nothing left over and nothing needed. And so that meant that that reaction, the skeleton equation, was already balanced. Next, we'll look at an example of a reaction that will require balancing. This is a reaction between vinegar and a screw that has a zinc coating. And so the word equation is going to be that acetic acid reacts with zinc to produce zinc acetate and hydrogen gas. You'll see the hydrogen gas as bubbles coming off of the screw. I've put in a finishing nail on the other side to contrast that, to show you that not all metals react moderately quickly with vinegar, that zinc is a more reactive one. Next is to come up with the skeleton equation, which means that we need to come up with the correct chemical formula for all of the reactants and the products. As we did before, we knew what acetic acid was because we looked at a reference and we found that acetate, the root of acetic acid, has a 1- charge, and so as an acid, gets an extra hydrogen added to it. It is only reacting with zinc metal, and so it is just the element zinc. Then we would have the arrow to show that we are working on products. Zinc acetate. We look at the charge for zinc and acetate because it's an ionic compound and they need to be neutralized based on their charge. You can see that the charge for zinc is 2+, and recall that the charge for acetate is only 1-. And so we need to have 2 acetate ions for every 1 zinc ion in a single zinc acetate formula unit. For hydrogen gas, the other product, the bubbles that are coming off, hydrogen gas is one of the diatomic elements in the Hofbrinkel mnemonic. Now people think that it's silly to have Hofbrinkel as a mnemonic, to remember that hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine are all diatomic and have that element and a subscript 2, but it's no more silly than remembering Roy G. Biv for the colors of the rainbow. And finally, for the skeleton equation, we'll need to look at the phases. As stated earlier, acids are always dissolved in water and will therefore be aqueous. The zinc metal, you can see that it is a screw, and you can also look on a periodic table to find that zinc at room temperature as an element is solid. Next, the zinc acetate. You can see that there's nothing in the water, it looks clear, and so you can know that the zinc acetate is dissolved. It too will be aqueous. Otherwise, you could look on a chart of solubilities and see that zinc acetate is soluble in water and so will be aqueous. And lastly, the hydrogen gas, you can see they are bubbles, but again, hydrogen, the element, you can look on a periodic table and see that at room temperature, it is a gas. What we'll look at now is why this skeleton equation needs to be balanced. This is a model of acetic acid and zinc. These are bottles of the products, zinc acetate and hydrogen gas. Now you can see that there's no way that those starting products, those reactants, those atoms, could be rearranged to make these products. It just doesn't add up, and it is therefore not balanced. What needs to happen is that multiples of things need to be added. And so instead of having just one acetic acid, to make sure that there are the same number of atoms of everything on both sides, there actually need to be two. The way to represent that is with a coefficient, with a 2 in front of the entire substance. That is a coefficient and is a multiplier for the entire thing. Now you can see that those things now can be rearranged to make the final products shown previously.